Hello everyone. In this video, I'm going to show you how to read values and count pulses from a Quadrature encoder motor using the ESP32 dev module. If you're new to my channel, make sure to subscribe and turn on the notification bell so you don't miss any of my upcoming videos. Let's talk about the electronic shop 𝐬𝐿𝐿, which offers a wide range of electronic kits for IoT, displays, and STEAM projects to make your making journey easier. They also provide custom PCBA manufacturing for both prototypes and production, along with 3D printing and manufacturing services. In this project, I'm using a 25GA gear motor with a built-in encoder. This motor has 6 pins. 2 pins are used to power the motor, while the remaining 4 pins are dedicated to powering the encoder and carrying the encoder signal output. Now, let's understand how a magnetic encoder works. A magnetic encoder consists of a rotating permanent magnet connected to a shaft and a stationary magnetic sensor, such as a Hall effect sensor, mounted on a PCB. As the magnet plate spins along with the motor shaft, the sensor detects variations in the magnetic field. An encoder works by detecting these magnetic field changes produced by the magnet on the motor shaft. When the motor rotates, it periodically generates outputs based on the direction of rotation. If the magnet rotates clockwise, output A is triggered first, and if it rotates counterclockwise, output B is triggered first. This behavior is extremely useful for controlling and managing the forward and reverse motion of a DC motor. I then mount an ESP32 on a Vero board and make all the necessary connections between the ESP32 and the encoder signal pins for both motors. After that, I connect the ESP32 to the computer using a USB cable. One important point to note is that the encoder pulse calculation code must run continuously without blocking the main program. Since the ESP32 is a dual-core processor, it can execute multiple tasks simultaneously on 2 independent cores. Core 0 is mainly responsible for system tasks, Wi-Fi or Bluetooth, and system task, while Core 1 runs user applications. By default, the Arduino setup and loop functions run on Core 1. To ensure smooth performance, I use Core 0 exclusively for the encoder task so that the encoder code always runs in the background in parallel without blocking the main loop. Let's take a look at the main code. First, I define the GPIO pins that are connected to the Quadrature encoders. Then I declare variables to store the total pulse count for both the left and right encoders. I also use variables to remember the previous state of each encoder so that I can compare it with the current state and accurately detect the rotation direction. A task handle is defined to manage the encoder task running on a specific core of the ESP32. The Quadrature decoding function determines the rotation direction by comparing the previous and current encoder state. If the encoder follows the normal sequence of 00, 01, 10, and 11, the motor is rotating forward and the pulse counter increases. If the sequence is reversed, such as 00, 10, 01, and 11, the motor is rotating backward and the pulse counter decreases. If there is no valid transition, the counter value remains unchanged. This encoder task runs continuously on Core 1 of the ESP32 and constantly reads the encoder signals without blocking the main loop. In this task, I combine channel A and channel B into a 2-bit value, which allows me to represent the encoder state as 00, 01, 10, or 11. I read the current encoder state, compare it with the previous state, detect the rotation direction, and update the pulse counter accordingly. The same logic is then repeated for the right motor encoder. A small V-task delay is added to give the CPU a short break and prevent unnecessary overload. In the void setup, as the encoder outputs are open collector, so I enable the internal pull-up resistors to obtain clean digital signals. This completes the configuration of the encoder task on the ESP32 core. In the main void loop, I simply print the encoder pulse counts to the serial monitor for debugging and testing purposes. After that, I select the board as ESP32 dev module and upload the code to the ESP32. Now let's test the setup. As you can see, when I rotate the motor in the forward direction, the pulse count increases. When I rotate the motor in the backward direction, the pulse count decreases. This clearly shows that we get positive pulses for forward rotation and negative pulses for reverse rotation. Next, let's test the system at high speed. Here, I use a battery to power the motor, allowing it to rotate faster. As you can see, the motor is running in the backward direction, and the pulse count is decreasing. Now I reverse the power terminals to change the rotation direction to forward, and as a result, the pulse count starts increasing. So, everything is working perfectly, and you can use this system in robotics and automation applications where precise motor rotation and direction control are essential. That's it for today's video. Thank you so much for watching till the end.